Hey there, I'm James. I'm a machine learning developer and an AI enthusiast, and today I want to bring your attention towards a very special topic of machine learning called zero-shot learning. Zero-shot learning is relatively recent in the overall field of computer vision, but it's one of the more exciting topics right now. Now, contrary to what a lot of current machine learning algorithms do, zero-shot learning models can actually make predictions based on data that it wasn't trained on before. So what do I mean by this? Well, normally in machine learning, I'd normally only be able to make predictions based on the data that I've trained on. So let's use an image classifier as a simple example. Now in an image classifier, my data would just be a collection of images, and my labels would just be a collection of image labels. So let's say that I had an image classifier of, let's say for a dog and a cat. Now the way I would normally train this is I would feed dog and cat images into my model, and I would associate them with their respective labels of dogs and cats. But that means that my model should only be trained on how to classify dogs and cats. For example, if I just asked it to suddenly classify like a car or like a fruit, then it would probably do very poorly because there were no exact data images of those things, like a car and a fruit. And zero-shot learning doesn't act this magically, but it acts according to that principle to allow my model to act based on images that it hasn't even seen. It doesn't look like magic though, so how does it work? Well, the way that zero-shot learning works is that it actually uses an additional source of information called a word embedding, or rather a collection of word embeddings. So a zero-shot learning model will combine the usage of both images and something like a word embedding matrix so that it can better classify classes that it wasn't directly trained on. As a brief recap, a word embedding is basically a vectorized representation of a word. Normally in machine learning, words don't mean that much to the actual model. So we in turn will vectorize it to capture the semantic relationships between said words. So for example, two words that might be found commonly close together would be close together in Euclidean distance when vectorized. And when we do this, we can actually give words meaning to the machine learning model. Now, there are actually a variety of different methods that we can use to incorporate these word embeddings. One of the simplest and most effective is known as an algorithm called devise. And the way it works is it basically converts your image classifier into an embedding generator. So let's say that we're using the Safari 10 dataset and we pluck out an image of a car. Under the classic image classifier, we would try to associate this image with a car label. But using devise, we would actually try to use it to predict the word embedding of a car. And after we run our model through all of our data, we actually get pretty good at this. We generate some pretty effective embeddings. But the beauty of this here is that these embeddings can actually be used to classify images that the model wasn't directly trained on. Now let's say that I now feed an image of a battleship into our image classifier. Now the Safari 10 dataset only has ships as images, and it doesn't really specify anything further. But using this embedding generator, I can actually classify my battleship correctly to a certain degree. So how do I do this? Well, using my model, I will feed in this image of a battleship, and to classify, I will compare this word embedding that's generated from this battleship to all of our other label embeddings, or in other words, the word embeddings for all of our labels. So we can compare it to the word embedding of ship, but there are times where the word embedding of battleship will actually be closer to our predicted embedding. And what happens then is that, well, since the battleship embedding is the closest to our actual image of the battleship, then we've effectively classified a battleship correctly, even though the model wasn't directly trained. Now this is absolutely insane. Let's expand this to scale. What if we had 1,000 training classes and then use this to predict up to, I don't know, like 10,000, 20,000, or even 50,000 predicting classes? Like, that'd be insane. That'd be literally a 50 times increase in classification power, even whilst using the same data the entire time. Now, with the development of newer zero-shot learning algorithms, we are slowly increasing our accuracy and reliabilities of these kinds of models, so we may be able to soon see this in the future. If we could do this effectively, then we could drastically reduce the amount of data that we need for any kind of computer vision classification task. This is cool and all, but it's also cool to think that zero-shot learning is kind of adapting more of how humans actually see the world. we don't actually need, as humans, to see any particular image to get an understanding of what it might be. Using additional information, we can often make inferences without seeing an image directly. And this is kind of what zero-shot learning is doing. It's using a main set of training classes, but it's also using auxiliary information in the form of word embeddings to help make an inference on classifying what any image is. And I think that's one of the cooler aspects of zero-shot. Closing off, I hope you learned a lot about zero-shot learning in this video. It's a really exciting and relatively new field of computer vision, and yeah, it's just really exciting. So if you're interested, then I'd highly recommend you to read more into the literature behind the area. But yeah, until next time, peace out.